Hello everyone, my name is Subrata Samanta and I am from IIT Kanpur. So I am your tutor for the physics subject. So in the previous class we briefly summarized that the content what we have learned so far, and so in case of continuous charge distributions we will calculate we have to calculate the vector integral instead of vector sum, and the integral becomes, so the net electric field at some point P in the space, so in 1 over 4 pi epsilon naught the vector integral dq over r square r cap, right, in case of continuous charge distribution, right. So where r is the distance from dq to the field point, so where r is the distance from dq to the field point P, and r hat is the corresponding unit vector. Okay. So to complete the integrations, okay, so now we have to evaluate this integration, right, and this dq is a small element of charge. Okay, so we consider a small element, so basically the dq is the charge of a small element, charge of a small element. So for a length, or means that for a line charge distributions, okay, so linear charge distributions, so for linear charge distribution, dq becomes lambda times dl. The lambda is a linear charge density, right. So lambda linear charge density, and second one for the surface charge distributions, surface charge distribution dq sigma dA, sigma is the surface charge density, and the third one is the volume charge distribution, dq rho times dv, volume element, where rho is the volume charge density, So one is the distributions, another is the density, right, and dq is the small element, charge of a small element. So in case of line charge density, or means that the linear charge distribution, the small element with length dl. In case of surface charge distribution, the small element with area dA, okay, and in case of volume charge distribution, the small element with volume dV. Okay. So basically the depending on whether the charge is distributed over a length, area or volume. Okay. So once we know the dq, right, and we put this dq into these expressions, okay, so you get a dE. So this is a dE. So you start with this, by writing this dE, okay, for a small element dq, and in case of different charge distributions we first compute the dq, okay, that is the first step. Okay. Okay. So basically this one is the second step. So this is the first step. So this is the first step, this is the second step, okay. And the third step we put this dq into the expression above. So third step, substitute dq into the expression for dE vector that is written there. So okay. So now we use the coordinate system. Okay, the fourth step we have to use the coordinate system appropriate. So, you have to use an appropriate coordinate system. So, the fourth step, so use an appropriate coordinate system to simplify the calculations. Appropriate coordinate system to simplify the problem. So, it depends on the problems. Okay. So, we have to use which coordinate system. So, there is a mainly discuss so here only 3 types of coordinate system. One is the Cartesian, spherical and the cylindrical coordinate system, right. So, depending on the problems, so we have to use the appropriate coordinate system, and that's makes to simplify your problems. Okay. So, in case of Cartesian coordinate system, basically x, y and z in the Cartesian coordinate system, and the cylindrical coordinate rho phi z, and the spherical coordinate r theta phi. So, here we only discuss these 3 types of coordinate system. So, each cases the dl, that means the length element, it becomes dx or dy or dz, okay, depending on the direction in which axis you are considering. And in case of cylindrical coordinate system, this one becomes d rho, rho d phi, okay, and dz. So, we use so this one is a d phi. So, if we use a 2D plane, okay, so then we only consider these two, okay, d rho and rho d phi. But if you consider a 3D system, we have also considered a z component, right, that is the dz. And in spherical coordinate system, dr, r d theta and r sin theta d phi. So, again, so if we consider a 2D things, so they become same, okay. Coordinate system and cylindrical coordinate systems, or is a planar coordinate system if we consider a 2D things, right. So, when you increase this 2D to 3D, okay, then the cylindrical coordinate system, and now you look into the difference between the cylindrical coordinate system and the spherical coordinate system. Similarly, the area element dA. So, in Cartesian coordinate system, the area element, if we consider the xy plane, so area element dx dy. If we consider the yz plane, the area element dy dz. If we consider the xz plane, the area element dz dx, right. In the cylindrical coordinate system, the area element becomes d rho dz, okay, the rho z things, or rho d phi dz, or rho d phi d rho, right. So, any multiple of 2, right. So, this one, we multiply this, multiple of any 2 small element, we give it 3 different area element. Similarly, in case of spherical coordinate, we get r dr d theta, r sin theta, dr d theta, so dr r sin theta d phi, so dr d phi, and r square sin theta d phi d theta, and d phi d theta d phi. Okay. Similarly, if we write the volume element, so there is only one terms there, because we consider 3D system, so volume is the largest. So, this one becomes dx dy dz, and this one becomes rho d phi d rho dz, this one becomes r square sin theta dr d theta d phi, right. So, once you know this element dl dA dV in case of 3 different coordinate systems. So, the fifth step, we rewrite dE in terms of the integration variable depending on the coordinate system. So, if your integration variable dx, dy or dz, right, in case of Cartesian coordinate system. So, rewrite d in terms of the integration variable and the next thing, apply the symmetry argument. This one is important. Apply the symmetry argument to identify non-vanishing component of the electric fields. Components of the electric field. Okay. So, this is a crucial point. Okay, this is symmetry argument. So, basically if we choose a coordinate systems, okay, and that is appropriate for your charge distributions. So, it is easy to identify it by the symmetry argument that which components are non-zero. If we choose a wrong coordinate systems, this kind of symmetry arguments cannot apply. Okay. So, we choose a proper coordinate system for your problems. Okay, then we use the symmetry argument to identify the non-vanishing component easily. Okay. And then the complete the integration. The last step is the complete the integration. So, to obtain the electric field, net electric. So, let us discuss on problem. So, let us say line charge density, right, that we already discussed in the class. So, we consider a line charge distributions over a rod of length L, okay, and draw the axis. This one is x, this one is y. So, this is the origin. So, it placed middle, okay, at the origin. The rod placed the middle point of the rod coincide with the origin of the coordinate system, and the length of the rod, its length is L, right. This one is L, the length, okay. And we calculate the point, let us say on the y axis at a point P. So, again we consider a small element. So, let us say this is this one, okay, at a distance x prime and dx prime, and the distance from the point P to this small element is r prime, okay, and angle is theta prime, right, with the y axis. So, then the first step, we rewrite the electric field at a point P due to this element with charge dq. So, we write this. The first step, d vector, we write 1 over 4 pi epsilon naught dq by r prime square, right, and r prime cap. Second step, we rewrite the dq in terms of the charge density. So, dq is lambda, here the dx prime, okay. So, the small strip, okay, have width dx prime, okay. So, since this is a linear system, we use a Cartesian coordinate systems, and that becomes clear in a moment. So, this one is the dq, and then we write down the again du in terms of dq. The third step, d is 1 over 4 pi epsilon naught lambda times dx prime over r prime square. Okay. So only consider the magnitude. So now we rewrite. So the fourth step, we rewrite r prime in terms of x and y, because we use the Cartesian coordinate system, right. So this r prime is the distance from the point P to the element, small element dq, we write in terms of x and y. So then the r prime square, x prime square plus y square, right, and cos theta. So this theta prime becomes y, if we denote this distance y over r prime, right. So now we apply the symmetry argument. So we apply the symmetry argument at this point P. So we say that for the small element dq with charge dq, the electric field in this direction, the radially outwards. Similarly, if we consider the small element just opposite to this dq, so also a dq charge, and due to this the electric field vector just like this. So this is, let us say, d vector due to this area element, let us say this is called 1 and it is denoted by 2, d1 d2. Which is the Cartesian coordinate system. So this d1 and d2 we can express in terms of x and y, okay, and it is easy to see that the y component cancel each other, sorry, x component cancel each other and the y components are only non-zero. So the dy is only non-zero. By symmetry argument, this becomes d cos theta. So here we use the dq as a continuous variable, so that is why we are not summing up, okay, so you have to integrate. So then we know the d, so this is the d, so just plug in here, okay, so plug into this here, so k, okay, so I write down the Coulomb constant 1 over 4 pi epsilon naught times lambda y. So now cos theta prime, so this one is a theta prime due to this element, so lambda y, and then dx prime x prime square y square 3 by 2, right. So on this here is r prime also, so from here we have to get this one, it becomes y over square root of x prime square plus y square. So the last step we integrate this, sixth step we integrate this, so we find a y ey, we integrate over dy, right. So basically we integrate over this dx prime, so lambda y over 4 pi epsilon naught dx prime x prime square plus y square. So here now the limit of x prime, so dx prime, so if you consider the dx prime at a distance x prime from the origin, so the limit of integration minus L by 2 to, so minus L by 2 to plus L by 2, okay. So the limit is important, because you consider the dx prime, the length of this element dx prime at a distance x prime from the origin O, right. So in this case the limit of this x prime is becomes minus L by 2 to minus this to this, okay, and then we finally found this 2 lambda over 4 pi epsilon naught y, and then L by 2 square root of L by 2 square plus y square, okay. So check this result. So in the next class we will solve more problems, okay, and that helps you to better understanding into the subject. Thank you.